Hello everyone. In today's lecture, we are going to solve some examples on how to find complementary function. So let us consider the examples. Find the general solution of differential equation d square y upon dx square plus 4 into dy upon dx minus 5y is equal to 0. So this is the given differential equation. To obtain general solution to this homogeneous differential equation as RHS is equal to 0, first we obtain its auxiliary equation, for which we need to replace this differential coefficient by the operator d. So therefore auxiliary equation will be d square plus 4d minus 5 is equal to 0. So here we have replaced this d square by dx square by capital D square, d upon dx by capital D, and we got the auxiliary equation as d square plus 4d minus 5 is equal to 0. Obtain the roots of this auxiliary equation. So roots are minus 5 and 1. So there are two roots as this is quadratic equation. These roots, now identify the nature of these roots. These roots, they are real and distinct as they are not same, and therefore general solution of given differential equation is y is equal to c1 e raised to minus 5x plus c2 e raised to x. So there are only two terms, each one is corresponding to each root. As there are two roots, we will be getting two terms in the general solution, and hence two arbitrary constants C1 and C2. And this number of arbitrary constants is equal to the order of differential equation, in this case which is 2. Now we will consider the next example. Find the general solution of the differential equation d square y upon dx square minus 4 into dy upon dx plus 4y equal to 0. Solution. First we obtain auxiliary equation, for which we replace this operator d square upon dx square by capital D square, d upon dx by capital D. Then we will take y common from the left hand side. So we left with a polynomial in D, that is phi of D equated to 0, which is D square minus 4D plus 4 equal to 0. This is the required auxiliary equation. Obtain its roots, which are D equal to 2 comma 2. Roots are real and repeated twice. Therefore, general solution to this homogeneous differential equation or the complementary function is y is equal to c1x plus c2 into e raised to 2x. So see, here we applied the case 2, that is when the roots are real and repeated, and for which, see, power of x that we have considered, it is the number of roots repeated. The root repeated how many times? Less 1. So here 2 is repeated twice, minus 1, so 1. So here we considered power of x as 1 plus c2 into x raised to 0, that is 1. So we got the term corresponding to these repeated roots as c1x plus c2 into e raised to 2x. So this is the general solution to this homogeneous differential equation. We will go to next example now. Find the general solution of the differential equation d raised to 4y upon dx raised to 4 minus 3 into d cube y upon dx cube plus 3 into d square y upon dx square minus dy upon dx is equal to 0. Again, get the auxiliary equation, for which replace this d raised to 4 upon dx raised to 4 by capital D raised to 4, this d cube upon dx cube by capital D cube, d square upon dx square by capital D square, and this d upon dx by d. and take y common. So whatever phi of d we left with, equate it to 0. So that will be auxiliary equation, which is d raised to 4 minus 3d cube plus 3d square minus d is equal to 0. Now we want to obtain roots of this auxiliary equation. For that, we will take d common, and in the bracket we left with d cube minus 3d square plus 3d minus 1 is equal to 0. Now this is the standard formula for d minus 1 whole bracket cube. Now we got both the linear, we have expressed the auxiliary equation into the linear factors. Now equate them to 0 and get the roots. So roots are 0, 1, 1, 1. So there are total 4 roots, and see here the degree of the auxiliary equation is 4. We got 4 roots, out of which this 1, all the roots are real roots, out of which this root 1 is repeated 3 times. Again, recall the case from the last lecture. When the root is repeated 3 times, then how we are obtaining the general solution. So first we write the term corresponding to 0 and then term corresponding to this repeated roots. Therefore, the general solution is y is equal to c1 e raised to 0x. So this is the term corresponding to root d equal to 0 plus. Next, now we have to continue the number of arbitrary constants. So as already we have used c1 here, now we will continue with that. Now next c2. As root 1 is repeated 3 times, consider the power of x less 1. So x square. So c2 x square. Now reduce the power of x by 1 until we get the constant term. So c2x square plus c3x plus c4 into e raised to 1x, that is e raised to x. So which is the required general solution. E raised to 0x is 1. Therefore, the final general solution is y is equal to c1 plus c2x square plus c3x plus c4 bracket complete into e raised to x. So in this way, we can obtain general solution to the homogeneous differential equation from roots of the auxiliary equation. Okay, now we will go to the next example. Find the general solution of the differential equation d raised to 4y upon dx raised to 4 plus 2 d cube y upon dx cube plus d square y upon dx square is equal to 0. Obtain the auxiliary equation, which will be d raised to 4 plus 2d cube plus d square is equal to 0. Now, d square is the term with minimum power in the auxiliary equation. So take it common, and therefore in the bracket we left with d square plus 2d plus 1 into d square is equal to 0. Now again this is the standard formula, which is the square of d plus 1 bracket square. Therefore roots are d equal to 0 0 minus 1 minus 1. Here we got total 4 roots, out of which 0 is repeated 2 times and minus 1 is repeated 2 times. And therefore, what will be this general solution? So corresponding to 0, term will be c1 plus c2x into e raised to 0x plus, and the term corresponding to minus 1 is c3x plus c4 into e raised to minus x. Now e raised to 0x is 1, therefore final solution will be y is equal to c1 plus c2x plus c3x plus c4 bracket complete into e raised to minus x. So in this way we can obtain the general solution to the given differential equation. Now we will consider the another example where we will be getting complex roots. For that, consider the differential equation d square plus 1 bracket cube into d square plus d plus 1 into y is equal to 0. So already it is given in the operator form and we just have to obtain roots to this auxiliary equation. So auxiliary equation is d square plus 1 bracket cube into d square plus d plus 1 is equal to 0. So obtain the roots to this auxiliary equation. If we equate d square plus 1 cube equal to 0 into d square plus 1 plus d plus 1 is equal to 0. Simplifying it, we will be getting roots as plus minus I, plus minus I, plus minus I. So these are the roots corresponding to the term d square plus 1 bracket cube equal to 0 and minus 1 plus minus I root 3 upon 2 are the roots corresponding to the term d square plus d plus 1 equal to 0. So there are total 8 roots out of which I is repeated 3 times and minus I is repeated 3 times. So this auxiliary equation is having complex roots which are repeated 3 times and there are two more complex roots which are distinct. They are minus 1 plus I root 3 upon 2 and minus 1 minus I root 3 upon 2. So there are total 8 such roots. So recall the procedure of obtaining general solution to the given differential equation when roots are complex roots which are distinct as well as which are repeated roots, and therefore the general solution will be given by, as this plus minus I is repeated 3 times, so corresponding to that term in the general solution will be c1x square plus c2x plus c3 into cos x plus c4x square plus c5x plus c6 into sin x. Whole bracket complete e raised to 0x because here real part is 0 and that e raised to 0x here considered as 1. So see, these total they are 6 roots and here we got 6 arbitrary constants. We are having 2 more complex roots corresponding to that. Now here alpha is minus half and beta is root 3 upon 2. So depending upon that, we will be getting the term as e raised to minus x by 2 into bracket. Now see, we have continued the number of arbitrary constant. So c7 into cos of root 3 upon 2 into x plus c8 into sine of root 3 upon 2 into x. So this is the required general solution to the given differential equation, and this is the case when roots are complex roots. In that case, how to obtain general solution to the given differential equation. I hope through all these examples you understood this topic, that how to obtain the complementary function or general solution to the given differential equation. Thanks for watching this video. For particular integral, how to obtain particular integral, please see next lecture. Thank you.